All right, let's just jump straight into it. In physics, there are some ideas that feel like, well, like they're carved in stone, absolute bedrock. But what if one of the biggest ones is actually built on sand? In this explainer, we're going to look at a pretty wild challenge to one of the most fundamental rules in the entire cosmos, the Virial theorem.
I mean, think about it. What holds a galaxy together? It's one of the most massive questions you can even ask, right? When you look up at those pictures of a swirling galaxy, or a star, or a whole cluster of stars, what's the cosmic glue stopping it all from just flying apart? It's this incredible, delicate balancing act of just immense forces.
And for decades, a huge part of the answer has been something called the Virial theorem. You can think of it as the universe's energy rulebook. It's the principle that explains how the outward push of motion, that's kinetic energy, is perfectly balanced by the inward pull of gravity, potential energy. It's what keeps these massive systems stable and not just, poof, gone.
But here's the kicker. What if it's wrong? I'm not talking about a little tweak. A physicist named Miles Mathis hasn't just questioned it. He's published work claiming the entire theorem is flat out false, from the math all the way to its conclusions, and he is not being shy about it. He's throwing down the gauntlet big time.
Okay, so here's what we're going to do. We're going to unpack this challenge. We're going to walk through Mathis's main arguments against this cornerstone of physics. We'll look at his claims neutrally, just to really understand why he thinks it's so fundamentally broken.
So first, let's just do a quick refresher on what this thing even is. The Virial theorem, at its core, says that in a stable system held together by gravity, the total potential energy is actually twice the total kinetic energy. It's the energy budget for a galaxy, you know? It tells us how that outward push of motion is kept in check by the inward pull of gravity.
All right, so Mathis's first big attack goes right for the jugular, the math itself. He calls the calculus used to derive the theorem, and this is a quote, a horrible fudge. So what's so horrible about it? What's the problem he's seeing?
So here's the core of his mathematical beef. Imagine you're trying to figure out a marathon runner's speed, okay? But the only evidence you have is a bunch of photos of them standing perfectly still at the starting line. It's impossible, right? You can't measure speed if nothing is moving. Mathis says the standard proof of the theorem does exactly that. It tries to calculate velocity by measuring the change in a particle's radius over time. But he's like, wait a minute. In a stable system, like a star, that radius is constant. The particle isn't moving out or in.
And here it is in his own words. You can't find a rate of change of a distance r since there is no change. So his claim is that the math literally invents motion where there isn't any, which would make the entire proof completely invalid right from the very first step.
But look, his problem with the calculus, that's just the opening salvo. His next argument? This one's good. It centers on a single, tiny, seemingly harmless number that could have absolutely giant consequences for physics.
This little guy, the number 2. This is the number in the Virial theorem. It's what says a system's potential energy is twice its kinetic energy. It's the whole key to that energy balance we were talking about. But Mathis is asking a very simple question. Where does this 2 actually come from?
Well, according to Mathis, this number comes from a mistake that's centuries old. He claims the standard formula we all learned for centripetal acceleration, that's the force keeping an object moving in a circle, is just plain wrong. He argues that because of an error in a proof by Newton himself, the correct formula should actually have a 2 in the denominator.
And here's where it gets crazy. If you make that one correction to the acceleration formula when you're deriving the Virial theorem, poof, the factor of 2 completely vanishes. It's just gone. And that would mean kinetic energy and potential energy aren't in some 1-to-2 ratio. No, they should be equal. This would completely rewrite the energy balance of every single star and galaxy we've ever studied.
And he's not done yet. The attacks just keep coming. Mathis's third big critique targets the very foundation the theorem is built on. He says it's all tied to a concept that is, frankly, a distraction. Spin.
So the classic way you derive the Virial theorem starts with a thing called the moment of inertia. The easiest way to picture this is a figure skater. You know how, when their arms are spread way out, they have a high moment of inertia and spin kind of slowly. Then they pull their arms in, their moment of inertia goes down, and whoosh, they spin way faster. It's all about how an object's mass is spread out when it's rotating. And that, according to Mathis, is the whole problem.
By starting the proof with a concept that is all about rotation, the Virial theorem becomes fundamentally tied to spin. He thinks this is like using the wrong tool for the job. Trying to hammer a nail with a screwdriver. Why are we building a theory about gravity on a foundation of spin?
Which leads to this really powerful question. Does gravity itself actually require spin to work? I mean, an apple falls straight down toward the center of the Earth, whether the Earth is spinning or not, right? The gravity is just there. So Mathis argues if gravity is the main force we're talking about, and it doesn't need spin to do its thing, then a theorem about gravity shouldn't be built on a concept of spin in the first place.
Okay, so this brings us to the big one. What if he's right? If these critiques are actually valid, if the math really is a fudge, if the 2 is a historical error, and the whole foundation is flawed, what happens then? What are the consequences? Well, in Mathis's own words, it's a complete knockout for modern physics.
So, what's the big deal? Why should you care if this one theorem, a tool that physicists have been using for over 100 years, is actually wrong? Well, the implications they're staggering. They ripple through pretty much every field of modern physics.
I mean, look at this. If the theorem is wrong, our estimates for dark matter could be wildly overestimated. Our entire understanding of how dead stars like white dwarfs stay stable would be wrong. It would compromise the Lagrangian and the Hamiltonian, and those are basically the fundamental rulebooks for everything from classical mechanics to quantum mechanics. It would, and this is no exaggeration, force us to rewrite 200 years of physics.
Let's just zoom in on the biggest one, dark matter. The Virial theorem is one of the main ways we calculate how much mass a galaxy needs to hold itself together. Astronomers look out there and see galaxies spinning way too fast for the amount of visible matter they have. So they say there must be this extra invisible dark matter providing the gravity. But Mathis argues that if kinetic energy is actually 100% higher than the theorem predicts, then suddenly you don't need to invent nearly as much missing dark matter to explain that gravitational pull.
Now, in the end, whether Miles Mathis is right or wrong, well, that's not for us to decide here. His challenge is incredibly provocative, and let's be clear, many in the mainstream would strongly, strongly disagree with him. But his critique is such a powerful reminder of what science really is. It's a process, not a destination. It shows us that even the most established bedrock ideas are not sacred, and that sometimes the biggest challenges are the very things that push our understanding of the universe forward.